Today, we're diving into expert systems and knowledge-based AI, exploring how computers can mimic human intelligence. Our focus will be on how these systems achieve their goals by mimicking human expertise through structured knowledge. Let's begin by understanding the core concepts behind rule-based systems, a fundamental type of expert system. These AI systems are primarily driven by predefined rules and facts, guiding their decision-making processes. We'll examine the essential components that make up a functional rule-based system, working together seamlessly. The knowledge base is crucial. It contains all the rules and facts that the system uses to perform its tasks. The inference engine acts as the brain, applying these rules to the available facts to arrive at logical decisions. Rules are typically structured as if condition then action statements, dictating the system's behavior. Facts are the pieces of information or data that the rules use to evaluate conditions and trigger actions. Now, let's look at some key characteristics that define rule-based systems, understanding their strengths and weaknesses. They are often simple to understand because their underlying logic is quite transparent and straightforward. The decision-making process is transparent, meaning you can easily trace how a conclusion was reached. However, they often have limited flexibility and may struggle to handle situations involving ambiguity or nuance. Maintenance can also be a challenge, as the set of rules grows larger and more complex over time. Next, let's walk through the steps involved in building a practical and effective rule-based system. This journey takes us from gathering expert knowledge all the way to validating the system's performance. The first critical step is knowledge acquisition, where we gather expertise from human specialists. Following that, we move to rule definition, meticulously translating that acquired knowledge into precise if-then rules. Then comes system implementation, where these defined rules and facts are coded into a functional system. Finally, testing and evaluation are crucial to ensure the system performs accurately and reliably as intended. Now, let's explore fuzzy logic, a fascinating approach to reasoning that deals with degrees of truth. Unlike traditional logic, fuzzy logic allows us to move beyond simple binary true or false statements. Let's start by defining what fuzzy logic truly means in the realm of artificial intelligence. It's an extension of classical logic, designed for reasoning with partial truth values, not just absolute ones. The basic concept involves using degrees of membership, ranging from 0 to 1, instead of strict binary values. This allows for more nuanced representation, where something can be partially true or partially false. Fuzzy logic has many practical applications, especially where precise, crisp data is unavailable or difficult to define. It's ideal for control systems and decision-making scenarios where there's inherent uncertainty or vagueness. Central to fuzzy logic are fuzzy sets, which are different from conventional sets you might be familiar with. These are sets without sharp boundaries, where elements have varying degrees of membership, reflecting real-world imprecision. Today, we'll explore fuzzy membership functions, a core concept in fuzzy logic for handling uncertainty in data. These functions are crucial for mapping crisp inputs to degrees of membership within fuzzy sets, making systems more flexible. Let's begin by looking at a common type, the triangular membership function, which is simple yet effective. The formula for the triangular function is mu of x equals the maximum of 0 and the minimum of 2 linear segments. Here, mu of x represents the degree of membership for a given input value, x, within our fuzzy set. The parameters a, b, and c are critical, as they define the precise shape and location of our triangular curve. This formula specifically defines a triangular membership curve, which starts at A and ends at C. For any input x, it achieves full membership, meaning a value of 1, exactly at point B, the triangle's peak. From point B, the membership value decreases linearly as x moves away towards either point A or point C. Next, we have the Gaussian function, which offers a smoother, more natural curve for membership representation. The Gaussian formula is mu of x equals e to the power of negative x minus c squared, all divided by 2 sigma squared. Again, mu of x denotes the degree of membership for your input value, X within the fuzzy set. In this formula, C is the center of our bell-shaped curve, indicating where membership is highest, and sigma, or standard deviation, determines the width of the curve, controlling its spread and fuzziness. This particular function defines a smooth, continuous, and bell-shaped membership curve, often seen in natural phenomena. Similar to the triangular function, input X achieves full membership, a value of 1, precisely at the center C. However, unlike the triangular, membership decreases smoothly and gradually as X moves away from the central point C. Now, let's walk through the entire fuzzy inference system process, step by step, to understand its workflow. The process begins with crisp inputs, which are precise, real-world numerical values that our system receives. Next, we have fuzzification, where these crisp inputs are transformed into fuzzy sets using membership functions. Following fuzzification, we move to rule evaluation, where fuzzy rules are applied to determine output fuzzy sets. Then comes aggregation, which combines the results of individual rule evaluations into a single fuzzy output set. Defuzzification is the next crucial step, converting the aggregated fuzzy output back into a crisp, usable value. Finally, we arrive at crisp outputs, which are the precise, actionable numerical results produced by the system. Today, we're comparing ontologies versus semantic networks, two powerful methods for knowledge representation in AI. Both are vital for structured knowledge representation, helping AI systems understand and reason about information. Let's first discuss ontologies, which provide a very formal and rigorous way to organize knowledge. Ontologies are formal representations of knowledge, detailing concepts, their relations, and specific instances clearly. They are highly structured, defining precise relationships and constraints between concepts, ensuring consistency. Ultimately, ontologies provide a shared understanding of a domain, both for human users and for AI systems. On the other hand, we have semantic networks, which offer a more visual and flexible approach to knowledge. These are graphical representations, using nodes for concepts and edges to show the relationships between them. Semantic networks are flexible and highly visual, focusing on showing graphical associations between ideas. They are particularly useful for visualizing and reasoning about complex relationships among various concepts. Now, let's explore some real-world applications of knowledge-based AI across various sectors and industries. Knowledge-based AI has a diverse impact, bringing significant advancements and efficiencies across many industries. In healthcare, it powers diagnostic systems, helping doctors with treatment suggestions and patient care. For finance, knowledge-based AI assists with credit risk assessment and plays a crucial role in fraud detection. In manufacturing, these systems enable advanced process control and help optimize automated production lines efficiently. Customer support benefits greatly from automated help desks and intelligent systems for troubleshooting common issues. Finally, in natural language processing, knowledge-based AI is essential for understanding and interpreting human language. All right, let's now summarize everything we've covered about expert systems and knowledge-based AI in this module. Here are the key takeaways and important points that you should definitely remember from our session today. First, rule-based systems are fundamental, using if-then rules for transparent and explainable decision-making processes. Next, fuzzy logic is excellent for handling uncertainty by employing degrees of truth and membership functions effectively. Ontologies provide a formal way to model complex domain knowledge, defining concepts and their intricate relations. Semantic networks offer a graphical representation of knowledge, connecting concepts through nodes and edges visually. Essentially, these AI systems are vital for enabling structured knowledge representation and advanced reasoning capabilities. Finally, remember their diverse applications, spanning critical fields like healthcare, finance, and control systems.